Hello, does this work? Yeah, good. There's a bit of an echo, so I'm going to try to talk differently, softly, louder, I don't know, until it works. Also, I have an accent, so if you don't understand me, please stop and ask me to repeat anything. I hope you're doing fine. The weather is working, which I hear is unusual for this town, this time of the year, so can't wait to get up there afterwards and talk to you all. All right, so first me, right? So I've been around for a while. I started as a grad student doing research on massively parallel grand challenge problems. We had huge numbers of computers, 64 sometimes. It was gigantic. Usually Digital Equipment Corporation alphas, which totally dates me. Probably most of you weren't born then. But the thing that was great at in the field at the time was that you could understand the whole system. All the way from the silicon, MOSFETs and all that, all the way to compilers, applications, operating systems. You could understand, a single person could understand the whole thing in one go. And I think that was really good for my obsessive-compulsive nature, a little bit. So for the rest of my career, I kind of remained anchored in infrastructure and, you know, like boring, detailed stuff. Even though I've worked at all sorts of places, I think that was the constant. I worked at big banks and small banks and big tech and small tech. Basically, I guess I got easily bored and I kept shifting around. I just arrived at a Web3 blockchain company 4 months ago. It's not because I wasn't interested in the field. I was interested since 2009. In 2020, I was running an Avanode. But the whole industry seemed a little bit of snake oil, a little bit too much hype to me. There didn't seem to be any kind of great, compelling use cases that were succeeding. But I think that's changing, so I'm here now. I think we're about to be really boring or really exciting, depending on what you find boring or exciting. I think getting the real economy to come into blockchain is really exciting, but people who like to, you know, take drugs and cruise ships might find it boring. I don't know. So I'm half an engineering. I'm not half an engineering manager. I'm one of 2 engineering managers in the platform engineering group. I'm not asking that you know what that is, but I'm going to try to show you a little bit. Let me start with a big picture. So this is a very schematic version of a possible network in Avalanche. These are the validator nodes with all the colors inside. We'll be zooming in soon. Just wanted you to show you that, you know, there is a huge data component that you heard about earlier today. In fact, more than half of our infrastructure, I think, is dedicated to this. And there's some tooling, and you know, this talks through the API nodes to all the nodes. And the nodes talk to each other through the P2P nodes, ports. Sorry. The whole thing might run in some cloud. It doesn't have to be a single cloud. It doesn't have to be AvaCloud. But you know, you've heard about this yesterday as well, both here and in the stage over there. I forget what it's called, showcase or whatnot. So this is the large picture, and our team is focused only on that little piece. And not even that little piece. I'll get to that soon. So this is the main consensus box, right? I mean, it's very big, and actual code is not the biggest piece, but it's the most important piece. And that supports 3 very important chains, P, X, and C, which you're probably familiar with, plus all the other ones on top. P, X, and C are special because they run in the same binary, right? So this is inside the binary. This line is the Avalanche binary, whereas the L1s are in separate processes talking through RPCs to the rest of the machinery. Our team is involved more in this. Of course, that requires supporting those. But what I'm going to talk about today is only this. Okay. The reason that I have that little thing in there is to denote some complexity. To get the Ethereum VM to run on a totally different consensus and so forth, and to make it happen quickly back in the day, we did some violence to it. So there's a lot of software complexity, some of it necessary, some of it not, that has evolved into a kind of a messy picture in that box, and that's part of what I'm going to tell you today. There's also ICM. ICM requires a lot of support for BLS signatures and so forth inside in our little world. But the ICM relays and a lot of the stuff that we just heard about is outside of the process, right? I should have drawn those in the cloud picture, I suppose, but I didn't. All right. This is not very important for the talk. It's just that if you talk to some of us, you might get confused, because we have an AvalancheGO team, which is different from the AvalancheGO binary. The AvalancheGO team is separate from the EVM team, right? So even though this is part of the binary, we have a different team for it. Now, we talk all the time, and of course, what these guys change will have an impact on those, and vice versa. So not a big difference, but talking to us, you might get confused. So that's why I have that there. All right, so I forget what this. Oh, yeah, just to tell you that you've heard about this before, right? So just put you into context that now I'm going to just go and talk about these. Okay, so before I tell you what we're planning to do, I think I need to tell you a little bit what we have done and why we have the trajectory that we have, because it's kind of interpolating or extrapolating the line, basically. So we're trying to build the best blockchain. I think we probably have succeeded. But what is a good blockchain? Look, well, first it has to be decentralized. That's the whole damn point. If it's not decentralized, we can just have a database run by some company, some centralized location. Databases can be parallelized and can perform really fast right today. So if you trust one person, you can just run one cluster of possibly thousands of database nodes, and you're done. It has to be low latency because you don't want to, you don't want to have to wait 5 minutes to pay for your coffee. It has to have scale because if we're going to subsume all of the economy, all of the real economy, we're not going to do that with something that a single computer can run, or a single chain. So that's why we have many blockchains that feel like one, which, by the way, you guys have it on your T-shirts, I think, right? I saw some. Yeah, that's pretty funny. Yeah, we didn't talk about it before that. Although you say chain, not blockchain, but that's my fault. And then you have to have throughput, of course, because again, if you're going to take over the whole economy, then you have to, have a lot of throughput on every single, not just in the aggregate, not only horizontally scaling, but also vertically scaling, so a single chain can process a lot of things. I'm going to go through this very quickly. I don't want you to focus on the details. To get this to happen, we've done a lot of work for many years. We've changed the consensus algorithms. We've changed a lot of logic. We've changed the staking rules and made them configurable. We created a new interface to talk to VMs. We added subnets first, which had to overlap the P-chain, and then we freed that constraint by creating L1s, which many of you are using, I think. And then also for the fast contracts, we've tried to improve the performance of the EVM. But as I said, we had to do some violence to it to make it happen. I know it's kind of low. And more recently, we also made the gas fees dynamic, which was a small amount of work, which had a great impact. Things are a lot cheaper now. People seem to be happy, so that's great. The reason I have these squares is because I'm going to talk about the constraints and the tech debt that they imply. Okay, so that's what we've done, and it's been great. We focused on the right thing, I think. We achieved what we achieved today by focusing on what we did. It's a little different from what we're going to focus over the next year, and that's why I want to put that in context. We have the best blockchain around, very scalable, sub-second transaction fees, and of course you're going to tell me how it sucks, and I hope you do, because usually we don't hear that side. So it's wonderful, but let me get out of the way. We have a lot of drag. We're trying to move fast, try new things like we always did, and we're finding that those 3 boxes there are slowing us down. We have the violence that we did to the EVM, means that we sometimes have taken in the past months to merge new versions of the Geth, of the Ethereum virtual machine. And also, all these changes, even though they've been done cleanly, have to remain around, because oftentimes we need to process all of the blocks from Genesis. Like if you join any validator, you might have to process everything. You might not have to, but you have to have all the code and be prepared to process everything, including blocks that were generated by consensus algorithms that are no longer there. So you have to keep all those algorithms around, and you have to keep a way of telling things apart and managing the whole damn complexity. So that's all slowing us down, and we're going to just put a knife through it and just cut down all those constraints. The first way we're going to do it is, there are 3 ways, right? So let me show you. Oh, I went back too far, but. So there are 3 efforts. One of them is here, one of them is here, and one of them is here, okay? So I'm going to go first through this one. There you go. So to avoid this thing where we have to go from Genesis and keep all the code around for all the historical reasons, we're going to Merkleize the storage. And again, I have to go through this quickly because I don't have a lot of time. If you don't know what that is, if you're interested, or if you know and you have questions, just come to me. or ask questions afterwards. And then once we have that, we can do dynamic state sync, so we don't have to start syncing at a particular checkpoint in time, and we can just adjust as we move forward. As we receive more blocks, as a validator is trying to sync to the network, it can adjust to the new blocks it's receiving without insisting on replaying everything. And then if we do that, we can delete a lot of codes. A lot of code makes the whole code base simpler, makes it easier to reason about, easier to test, and easier to add things to it. Also, it gets the nodes to join the network faster, but that is a really good side effect. The velocity will allow us to do all sorts of things. For example, and we're not committing to it or anything, we're just starting to talk about it, we could have a ROS version, perhaps, of Avalanche. Right now, that would be a huge effort, because we would have to recode all the historical consensus algorithms that we have worked on from scratch in Rust, and we're not ready to do that. We're not sure we're ready to do the simpler version either, but at least this enables that and many other things. All right, so the parts of the consensus, I think we've done a lot of work making consensus really good, so we have very few things to do. But there are a couple of them that are important, which are here. First one, I'm going to point out that your L1s need to refer to the block height on the P chain. Whatever, there is a dependency. So if the P chain is falling behind for whatever reason, your L1 might fall behind too. We want to isolate that, break that link, so your L1 can race ahead when, for whatever reason, we hope it never happens, but for whatever reason, the P chain is running slow. So we're going to do that by having acceptance proofs. Basically, your L1, one validator in your L1 will receive something that refers to a P chain block that it has not seen yet, or that it's not aware of. If it has an acceptance proof, it can say, OK, I haven't seen this, but I trust you. I trust that this thing will exist in the future. In my future, it already exists in somebody else's future, of course. And I'm going to just keep going with my L1 processing without waiting for the P chain to catch up in my local part of the world. And that will also require epoch views, which I'm not going to go into the detail for. And then the other thing that we're doing is, there's no reason for L1s and the P chain to share the same consensus algorithm. I mean, I know that in theory they don't have to already, but it's kind of not common and kind of a little difficult to change the consensus algorithm, plus you would probably have to write your own. And the fact is that L1s are very different from the P chain, right? First, they're usually smaller number of nodes. The nodes are usually bigger. They're usually more concentrated in space with better networks in between them. So maybe there is an argument to have a different consensus algorithm in those, and we have one such, Simplex. You're going to see a demo of it, and it says 20, it's probably more like 30 minutes. Yakov is somewhere around, and he's going to show you a version of it working, although the real production version probably is not going to be there this summer. Okay. Then the third piece, which is really what we're concentrating most of the company on, mostly because it's the thing that we have most neglected in the past, is the EVM. Because our scale doesn't come from, like, I don't know, Solana, etc. It doesn't come from having one EVM go really fast, right? Our scale comes from many chains that feel like one, I think. That's right? Yeah, OK. So we have done that hard part first, and now we're going to do the easy part, quote-unquote easy. The first thing that we need to do is to get rid of all this stupid software complexity, and we have something called libEVM, which we're going to hear about tomorrow at 11:25, right here, which is just a kind of, in my opinion, kind of brilliant, but it's kind of boring because it's just refactoring software to some extent, where we isolate the pieces of Geth that we need to modify, make them into, you might call them callbacks, I suppose, so that you need to modify the least amount of lines of code in Geth, isolate them, put them in a few files, source files, and then that allows the merges to go through very easily. And then, so you have, basically you minimize the impact that you're having on the Geth source so that we can merge new versions of Geth very quickly. And we're going to use that for the first time to apply Pectra. Instead of taking us 6 or 7 months like it's taken in the past, hopefully it will come. I mean, it says Q3, but it hopefully will be before the end of Q3, maybe at the beginning. We'll see, because we're kind of testing this software refactor to see how far it takes us. It's a big deal, though. Come back tomorrow. Then the perhaps biggest deal of them all is streaming asynchronous execution. We have a patent pending for that. So I'm again here. Come tomorrow and hear about it. I'm not going to go on and on about it at all, but it's basically a way of completely decoupling. I mean, I know that Solana and others have asynchronous execution, but this goes a step further in decoupling execution and consensus. Come tomorrow and hear about it. Oh yeah, there's another one, 2 more. First, we're replacing the database. Almost everybody uses LevelDB or some other LSMs like that. We're going to replace it with a custom database that is completely optimized just to store Merkle trees, to store the state of the EVM. And we have an advanced prototype that is already showing substantial speed up. Also, it will allow us to cut a lot of historical state, because one of the things we want to do is to decrease the storage footprint. Who knows, maybe one day we'll be able to run without disk at all, fully in memory, and that would definitely make us faster than any chain out there, right? So we're moving towards that in small steps. That's a side effect of using Firewood, though. Even storing the same amount of state, it will be a lot faster. And then finally, we're replacing, right now, all the information that the virtual machine needs is in just one big database. It turns out that blocks, right? Blocks are much bigger than most of the things you need to keep around. Also, their data access patterns are totally different, so they would totally benefit from having a separate database that is optimized for that sort of data access and size. So we're also writing our own custom database for the blocks. All right, this is the bulk of our work for the next few months. And I'm running late, Ron? Thank you, sorry about that. All right, that's the only take. Fast EVM, in fact, fast any VM. If we can run the Solana VM, it will be faster than that too. I'm not going to go through any of this. It's just other things that we're always thinking about, trying to prioritize them. We need you to tell us what is important to you. And if you have any questions about any of these, just let me know. Sorry I took too long. Yeah. Thanks.
I think we can take probably one question.
Really? That's amazing.
But let's just do it real quick if someone has anything.
No question. Oh, yeah.
Just.
Hi, I see in your slide that you didn't mention slush as Avalanche algorithm. So
Avalanche algorithms?
Yeah, slush. So you mentioned, snowball.
Yeah.
And the other. What about slush?
Remember that I just joined, but I think I was following the papers. I think slush was in a paper, but I don't think it was ever implemented. Somebody correct me if I'm wrong.
Running the XP and C chain, so in some way it is there.
Good job with the microphone.
Well, thank you so much.
Thank you.